Imagine a single processor that could boot classic Mac OS and then turn around and run Windows software natively, without emulation, without tricks, on the exact same chip. In the mid-1990s, that wasn't just a fantasy. IBM and its partners actually tried to build it. The project was called the PowerPC 615, and on paper it was one of the strangest and most ambitious CPUs ever conceived. A PowerPC processor with full x86 compatibility, baked directly into the silicon. If it had worked, a Mac could have been a PC, and a PC could have been a Mac, just by changing the operating system. The PowerPC camp wouldn't have needed to convince developers to rewrite their software. In theory, the chip would simply speak both languages, but that future never arrived. The 615 never officially shipped. It flickered in and out of obscure roadmaps, left behind a handful of technical hints and rumors, and then vanished as if it had never existed. In this video, we'll dig into the world that produced the 615, the radical idea at its core, the technical and political battles that shaped it, and why this everything chip ultimately became one of computing history's great what-ifs. To understand why anyone would attempt such a bizarre hybrid processor, we have to go back to the early to mid-1990s. This was the era of the RISC versus CISC wars. Intel's x86 chips, like the 486 and the first Pentiums, were CISC processors, complex instruction set computing, with a large, quirky instruction set that had evolved since the late 1970s. They powered the exploding IBM-compatible PC market and, crucially, ran Microsoft Windows and its rapidly growing software library. Opposing that world was the RISC camp, reduced instruction set computing. RISC designs like MIPS, SPARC, and IBM's Power emphasized simpler, more regular instructions that were easier to pipeline and optimize. On paper, RISC promised higher performance per clock and cleaner designs. In 1991, Apple, IBM, and Motorola formed the AM Alliance to bring RISC to the mass desktop market. Their weapon was PowerPC, a new architecture derived from IBM's high-end power chips but scaled down and adapted for personal computers. By 1994, systems like the Power Macintosh line were shipping with PowerPC 601 processors. Benchmarks showed impressive performance against contemporary x86 chips. Technically, the vision looked sound: cleaner architecture, strong engineering, and the backing of three giants determined to challenge Intel's dominance. The trouble was, you can't sell performance in a vacuum. While the AIM Alliance had a solid architecture, Intel had something even more powerful: software gravity. By the mid-90s, the vast majority of commercial applications, especially in business, were written for x86 PCs running DOS and Windows. PowerPC systems, whether Apple's Macs or IBM's own workstations, lived in a parallel universe of operating systems and binaries. Apple tried to bridge the gap. For classic Mac OS, they relied on a combination of fat binaries that could contain both 68K and PowerPC code, and software emulation to run older Motorola-based applications. That helped Mac users transition from 68K to PowerPC, but it didn't solve the bigger problem: the giant ecosystem of Windows software. Emulating x86 on PowerPC in software was technically possible but painfully slow on the hardware of the time. Early emulators were curiosities, not serious daily drivers. For IBM, the situation wasn't much better. Its PowerPC-based PCs and OS/2 dreams struggled because people simply wanted the familiar world of Windows and x86, where their programs and games just worked. So, even as PowerPC chips put up competitive benchmark numbers, they were locked out of the software people actually cared about. That pressure to somehow, someway run x86 code would become a defining strategic problem for the architecture. This is where the PowerPC 615 comes in. Instead of slow software emulation, engineers began exploring the idea of making x86 a first-class citizen in hardware, alongside the native PowerPC instruction set. The 615 was envisioned as a single processor core that could switch between executing PowerPC instructions and x86 instructions directly. Details are sparse and some are based on fragmentary documentation and secondhand reports, but the broad concept is reasonably clear. Rather than bolt on a separate x86 coprocessor, the 615's front end would have dual-mode instruction decoding. In PowerPC mode, it would fetch and decode fixed-length RISC-style instructions. In x86 mode, it would handle variable-length CISC instructions, including the quirky addressing modes, and legacy behaviors x86 carried from the 8086 era. Crucially, this is a different philosophy from the software translation and emulation we're used to. Later tools like Apple's Rosetta would take x86 code and translate it into another architecture's instructions in software, caching the results. In contrast, the 615 aimed to understand both languages natively in Silicon, toggle a mode bit, or perhaps jump through a special gate, and the core effectively reinterpreted the incoming bytes either as PowerPC or as x86. From the operating system's perspective, it would see something that behaved, instruction for instruction, like a real x86 CPU, not an emulator pretending to be one. If it worked well, you could, in theory, boot a PowerPC operating system, then reboot and run Windows on the exact same machine without any translation layer in between. The 615 wasn't designed in a vacuum. It sat alongside and partly in the shadow of more conventional PowerPC chips like the 601, 603, and 604. IBM took the lead on the 615, drawing from the same design culture that had produced the original Power processors and the first PowerPCs. The 601 was the transitional chip, bridging IBM's Power and the new PowerPC ISA. The 603 and 604 families pushed lower power and higher performance for mainstream desktops and workstations. The 615, by contrast, was never meant to be the fastest pure PowerPC core. It was a specialty part, a bridge. The idea was to target markets where x86 compatibility was seen as essential, but where IBM and Apple still hoped to promote PowerPC as the long-term architecture. For Apple, that painted an irresistible picture. Macs that could finally offer native Windows compatibility, not as a cluggy add-on card, but right on the motherboard CPU. For IBM, it hinted at PCs that could run standard Windows software, yet also serve as a migration path to a cleaner RISC architecture and IBM's own operating systems. There were also hints of interest for niche markets like servers or thin clients that might need to support legacy x86 workloads while transitioning to new PowerPC-based platforms. But publicly available specifics are thin, and much of the roadmap detail never left internal planning documents. What's clear is that the 615 was viewed as a strategic bridge chip, not the future of PowerPC itself, but a way to cross the software chasm between PowerPC and the entrenched x86 world. On paper, the idea of a dual-mode PowerPC/x86 chip sounds elegant. In practice, it's a minefield of engineering compromises. For one, x86 and PowerPC are fundamentally different in how they represent and process instructions. PowerPC uses fixed-length instructions and a load-store design. x86 uses variable-length instructions with dense encodings and a great deal of historical baggage. Building a single front-end that can efficiently decode both isn't just twice the work. It can distort the entire microarchitecture. The 615's designers would have had to allocate significant silicon area to x86-specific decoding and execution quirks, area that couldn't be used for larger caches, more execution units, or deeper pipelines. That pushes up die size and cost, in an era when every additional square millimeter mattered. Then there's performance. Making x86 correct at the architectural level doesn't guarantee that it's fast. Matching contemporary Pentium-class performance while also being a credible PowerPC core is a brutal balancing act. Go too far toward optimizing x86, and your PowerPC side looks weak compared to a pure 604. Focus too much on PowerPC, and you end up with an expensive chip that runs x86 code poorly, undercutting the entire point. Validation is another nightmare. Every x86 instruction, every odd corner case, every undefined behavior that real software secretly relies on, all has to behave exactly as expected. At the same time, your PowerPC mode must remain fully compliant with its own spec. That's effectively 2 full CPU validation efforts packed into one. We don't have a full, publicly available engineering postmortem on the 615, but based on what's known about CPU design and the era's constraints, it's clear that the hardware ambition here was extremely high, perhaps uncomfortably so. Even if the 615's engineering challenges could have been tamed, the business and political winds around it were changing fast. Apple, in the mid-1990s, was a company in turmoil. Leadership turned over, product strategies collided, and the company experimented with all kinds of ways to stay relevant against the tidal wave of Windows PCs. In that context, a hybrid PowerPC/x86 chip looked like a tempting strategic shortcut. But as the decade wore on, that thinking began to shift. When Steve Jobs returned to Apple in 1997, he brought a ruthless focus on simplification. Apple's new strategy centered on making the Mac compelling on its own terms, not by trying to be a better PC. Hardware-level x86 compatibility, while intriguing, didn't fit that vision. It threatened to blur the Mac's identity and entangle Apple even more deeply in the Windows world it was trying to differentiate itself from. Sources from the era suggest that enthusiasm inside Apple for exotic compatibility projects, including hardware hybrids, cooled noticeably as the company refocused. On IBM's side, PowerPC remained important, but the company's priorities were moving towards servers, embedded systems, and custom silicon, not risky desktop experiments. The dream of PowerPC conquering the Windows PC market was fading. As for Microsoft and the broader Windows ecosystem, there's little evidence of strong sustained support for a dual ISA PowerPC. From their perspective, Intel and the x86 clone makers were already delivering what they needed. Betting on a complex, unproven hybrid design offered them few clear advantages. In that changing environment, the 615 began to look less like a bold strategic bridge and more like a costly distraction. Unlike some high-profile canceled chips, the PowerPC 615 didn't get a dramatic public death. It simply faded away. The exact timeline is murky. Some internal and semi-public roadmaps from the mid-1990s reference the 615 or a related x86 compatible design. There are reports that silicon prototypes existed and that at least limited testing was done, but hard, detailed public documentation is scarce. Much of what's been written since relies on second-hand accounts and recollections. What seems reasonably clear is that by the late 1990s, any serious push to commercialize the 615 had stopped. The combination of engineering complexity, unclear market demand, and shifting corporate strategies made the project hard to justify. At the same time, the broader AIM alliance was losing momentum as a unified front against Intel on the desktop. Apple doubled down on the Mac and later charted its own course entirely. IBM refocused PowerPC on servers and embedded applications, eventually evolving it into the Power and Power-based ecosystems we see today. Motorola followed its own path, particularly in embedded and mobile. In that context, the 615 was a casualty of a larger strategic retreat. The dream of a mass-market, PowerPC-based rival to the Wintel world was slipping away. A complex, expensive hybrid chip with uncertain performance and no clear champion no longer fit the new reality. So the 615 joined the long list of almost products, technically fascinating, occasionally glimpsed in old slides and engineering anecdotes, but never given a chance to prove itself in the market. Although the PowerPC 615 never shipped, its core problem never went away. How do you move between processor architectures without abandoning your software? Over time, the industry largely answered that question not with dual ISA hardware, but with smarter software. On the PowerPC Mac, Apple leaned on emulation and developer tools to ease transitions. Later, when Apple moved from PowerPC to Intel in 2005, it introduced Rosetta, a dynamic binary translation layer that allowed existing PowerPC Mac applications to run on x86 Macs, often with surprisingly good performance. Years later, when Apple made the leap from Intel to its own ARM-based Apple Silicon, it repeated the trick with Rosetta 2, this time translating x86 64 code into ARM instructions. Thanks to massive increases in CPU performance and careful engineering, this software-based approach delivered levels of compatibility that would have been unthinkable in the mid-1990s. Virtualization and containerization also played a role. While not always crossing ISA boundaries, they showed that isolating and abstracting software environments could be a more flexible solution than hardwiring multiple instruction sets into one chip. In parallel, a few niche architectures have experimented with some degree of multi-ISA support, but true symmetric dual ISA cores like the 615 envisioned remain rare. The cost, complexity, and validation burden are enormous compared to improving compilers, translators, and emulators. In a sense, the 615 was a hardware-first answer to a problem that the industry ultimately decided to solve in software. Looking back, the PowerPC 615 feels like a product of its time, a bold attempt to brute force compatibility at the hardware level, before software and raw performance made other approaches more practical. It also illustrates why dual ISA designs have rarely become mainstream commercial products. Every instruction set you add multiplies your design and validation effort. It eats die area that could be spent on caches, cores, or power efficiency, and it locks you into the quirks of not just one but two architectural histories. Meanwhile, Moore's law kept delivering more transistors and more performance. That surplus made it increasingly attractive to spend some of that power on software techniques like dynamic translation and virtualization. Rather than carry x86 in silicon alongside PowerPC, you could just translate x86 into whatever your native ISA was and let your fast modern core do the rest. The 615 also underscores a strategic lesson. Architecture transitions are as much about business decisions, developer relations, and ecosystem planning as they are about clever silicon. Apple's later transitions succeeded not because of any single magic chip, but because they were managed CISC, tools for developers, clear timelines, and compatibility solutions that didn't require rewriting the laws of CPU design. So the PowerPC 615 remains an intriguing footnote, a glimpse into an alternate path where Macs might have booted Windows natively on a weird hybrid CPU, and where PowerPC might have had a second life as a stealth x86-compatible platform. Instead, it serves as a reminder that not every technically fascinating idea is the right answer, and that sometimes the most sustainable way to bridge architectures isn't to merge them in silicon, but to let software and time do the work. In the end, the 615's greatest legacy may be the question it poses: how far should we go, and how much complexity should we embrace in the name of compatibility? For the companies that quietly walked away from it, the answer was clear enough.